Hello everyone. Today we will explain to you the exercise and homework tree from linear algebra. Before we start our presentation, let us introduce ourselves. Started from me. My name is Danvi Almasrazqi Suwatno with student ID 24151010555, and there is my friend.
And me, Abiyan Azis with student ID 24151010557.
So without any further ado, let's get started to the presentation. Started from question number one. Question is proof that we check that W is a vector subspace of a vector space V. We only need to check the closure axiom. Explain why we don't need to check the other axioms. So there is a subspace vector theorem that says that to check that a vector is subspace, we only need to check axioma 1 or closure to addition and closure to scalar multiplication. And the theorem is true because those two conditions automatically guarantee that the other 8 condition or axiom are also satisfied to be the subspace. W must satisfy all 10 axiom of a vector space. So this theorem is an efficient shortcut. Why? Because 6 axioms are inherited, rules like commutative or distributive are already guaranteed to be true. And why? Because the vector of W are also vectors in phi, and they already follow the rules in phi. Because of that, we don't need to check them again. And then 2 axioms are focused, and the 2 axioms, the existence of U and minus U, is forced to be true. So the remaining 2 axioms, that closure under scalar multiplication and yeah, the addition of vector is forced to be true. For example, here is the zero factor. Since W is closed under multiplication by any scalar, we can choose the scalar k equals to 0. If U is in W, then uh, 0 multiplied by U will equal to 0. So 0 must also be in W. And then there's the additive inverse, like this, mean U. We can choose the scalar like K equals to minus 1. If U is in W, then minus 1 multiplied by U will be equal to minus 1. So minus 1 must also be in W. So therefore, by testing just 2 conditions, we can have actually proven all 10 conditions. 2 tested, 6 inherited, and 2 forced. And then there's question number 2. Prove that all vectors that lie on a straight line in R3 or interdimension from a vector subspace of R3 or vector in third dimension. So a line that passes through the origin of is proven to be subspace because it satisfied two main condition from the subspace theorem. That two main condition is the first one is closed under addition. So if you take any two vectors on the line and add them together, the resulting vector will still lie on the exact same line, and the vector will not break or move off its path. And the second is closed under scalar multiplication. If you take any vector that line and multiply by its scalar, like any number like 5 minus 1 or 0.5, the resulting vector, which becomes longer, reverses direction or becomes shorter, will also align on the exact same line because both of this operation never throw the result outside at the line. The line is considered a self-contained or closed system within R3 or vector in third dimension, which is the definition of a subspace. And then there's question number 3. Why does a plane passing through the origin In R3, have the equation of ax plus by and cz equal to 0, where a, b, c are the elements of R and x, y, z represent the coordinate of point in R3. Is this plane a subspace of R3? So, the equation ax plus by and cz equals to 0 is the mathematical way of stating perpendicularity. Why? First of all, every plane has a normal vector which we can call n equals to ABC. Second, because the plane passes through the origin, like 0, 0, 0, every point x, y, and z on the plane can be seen as a position vector phi equals to x, y, z that lies entirely on the plane. Third is the condition for phi to lie on the plane is that phi must be perpendicular to n. And fourth, in linear algebra, two vectors are perpendicular if their dot product is 0. The equation is the mathematical way of saying the set of all points x, y, z whose position vector is perpendicular to the normal vector, or ABC. I think that's all for me explaining the question number 1, 2, and 3. And the next question will be explained by my friend Abiyan. The stage is yours.
Thank you, Danvi, for the explanation for question from number 1 until 3. And now I will continue to explain the question for number 4 until 6. And for number 4, we have the question that create a set which S is equals to U, V, V is consisting of three linearly independent vectors in R3. From the first question, show that the system of linear equation for K1U plus K2V plus K3W equals to 0 that has one solution which is trivial. So namely as the question 0, 0, 0. And for the second, is this set a spanning set of R3? What is this set of R3? And then for the number 3, does the set of vector resulting from the linear combination of U, V, and W from a vector subspace of R3? As the question for the number 4 in the first question, which is consists of three independent linear vector in R3. So this means that the U is equals to 1 and 0, 0. And then for the V is equals to 0, 1, 0. And for the W is equals to 0, 0, 1. So this is the result of addition that we can set as a substitute of K1 until K3. And then for the result of addition that we have the 0, 0 for K1 until K3, this is the only way for this equation to be true is 0. For the K1 is equals to K2 and K3. So this proves that the three vectors are linear independent. Only the trivial solution has a linear combination of 0. Is the set a spanning set of R3? This is yes. If a space has dimension n, then every set containing n linearly independent vector is a basis. This means that span U, V, and V is equals to R3 for the entire space. R3 is a dimensional space and set S contains linear independent vector. Therefore, they span the entire space of R3. This is because it has three linear independent, which places vector in three-dimensional space. And then for the statement number 3, what is the set of vector result from a linear combination of U, V, and W from a vector subspace of R3. So for the W is equals to K1 until K3, and this is the linear combination set with element of R. So by the definition, W is equals to span of U, V, and W. The span of any set of vector is always a subspace of its parent space. So this is mean that it's closure under addition, and then the second is closure under scalar multiplication, and contain the zero vector for the operation are inherited from R3 because the span of U, V, and W is equals to R3. The result of linear combination is not only a subspace, but a subspace that is the same as the integral for the R3. And now we come to the question for number 5. Create a set S is equals to U, V, and W consisting of three vectors that are not linearly independent in R3. And now we have the SPL that K1U plus K2V plus K3W is equals to 0 has infinitely many solutions. So how are the solutions represented in parametric form? So for the question number 5, for the U is equals to 1, 0, 0, and V as 0, 1, 0, and W is equals to 1, 1, 0. We take the W as equals to U plus V, and for the K1 until K3 is equals to 0, so this is mean that K1 0, 0 plus K2 0, 1, 0 plus K3 1, 1, 0 is equals to 0, 0, 0. And then the system is obtained as K1 plus K3 is equals to 0, and then for the K2 plus K3 is equals to 0. We have seen that the solution is infinite from the system that K1 is equals to minus K3 and K2 is equals to minus K3. Suppose if K3 is equals to T as a free parameter, then K1 is equals to minus T and K2 is equals to minus T and K3 as equals to T. So because T is free can have any real value, there infinitely have many solutions with the T as a real parameter. So this can form as K1, K2, and K3 is equals to minus T and T. So the T substitute as the value of real parameter for K1, K2, and K3 is equals to T in the T minus 1, and 1. K1U plus K2V plus K3W equals to T minus U minus V plus W equals to 0 for each T. So this proves that the solution is not trivial. This is a free parameter for T and the solution is infinite. And now we come to the question for number 6. Is the set S that you form in question number 4 a basis of R3? In question number 4, we have been proved that three factors in R3 are linear independent. K1U plus K2V plus K3W is equals to 0. And then for the U is equals to 1, 0, 0, and V 0, 1, 0, and W 0, 0, 1. This is proof that the linear independence for the component that given in the question for number 4. So the first component K1 is equals to 0, and the second component K2 is equals to 0, and the third component produce K3 equals to 0. It is just a trivial solution in linear independence. And then for every x is equals to x1, x2, and x3, which element of R3 can be written as a linear combination that we can substitute for U, V, and W. As the result, that we have the x1U plus x2V plus x3W that we can substitute as the value for the question number 4. For x1, that we have the 1, 0, 0 plus x2 0, 1, 0 plus x3 is 0, 0, 1. And this is equals to that x1, x2, and x3 equals to x. For the span U, V, and W is equals in dimensional space of R3. So by the definition of basis, a set of vectors that are linear independent and span the entire space. So S is a basis for R3. So thank you that we have explanation for our team or group. We apologize for any mistake and shortcoming during the presentation if we have any mistake, and thank you for the attention.